Switching gears. A raw pretrained model just predicts text. It is not an assistant yet. So when you supervise fine-tune it, what does the training data even look like? Think of teaching by example. You do not lecture the model about being helpful. You show it thousands of times. Here is a request, here is the good answer. So the basic unit is a pair. One instruction, one response that nails it. The model reads the request and learns to produce that answer. Stack up a pile and you are set. But a conversation has parts, so we tag each piece with a role. The system message sets the rules, the user turn asks the thing, and the assistant turn is the answer the model is learning. Then you wrap those tagged turns in a chat template. It just marks where each role starts and stops, so the model always knows who is talking. Same recipe every time. And here is the part people sleep on. The format is not just tidiness. Train with one template, then prompt with a different one, and the model gets genuinely confused. Matching it does real work. So that is the whole shape of it. Instruction and response pairs sorted into roles, wrapped in a chat template. And you do not write them by hand. Open datasets like Open Assistant, Dolly, and Alpaca are ready to go. And the answer that gets you the offer is specific. Instruction-response pairs, structured into system, user, and assistant roles, formatted with a chat template. Naming those shows you have actually prepped the data. So go format a dataset yourself and run a real fine-tune. Watching your model turn polite is the fun part. The free notebook is in the bio. Here's a question that quietly sinks a lot of interviews. You're teaching a model to be a helpful assistant. Which words do you actually grade it on? Get that wrong, and it learns the wrong job. Think of a tutor with a kid. You don't grade the kid on reading the question out loud. You grade the answer they give. The question was never theirs to get right. In fine-tuning, each example is one long ribbon of text. The system message, then the user's question, then the assistant's reply, all stitched together. The lazy move is to train it to predict every word in that ribbon. But think about what that teaches. You're rewarding it for memorizing the questions people ask. You're burning its brain power learning to be the user, not the assistant. So here's the fix. You mask the prompt. You tell the loss to skip the system and user words, usually by tagging their labels with -100, the universal code for ignore this. Now the only words it gets graded on are the assistant's reply. So all that capacity pours into one skill, learning how to respond, instead of parroting the prompt back. And that's label masking. Same training math you already know, just pointed at the right target. Tiny detail, huge difference in what the model becomes. And here's what gets you the offer. Anyone can say set the labels to -100. The ones who get hired explain why. That capacity is a fixed budget, and you don't waste a drop of it modeling text the user already wrote. So don't just nod along. Go mask the tokens yourself and watch the loss change. The free notebook is in the bio. The interviewer leans in and asks, what's the actual loss when you fine-tune a chatbot? And people freeze like it's some scary new beast. Plot twist, it's the oldest idea in the book. At heart, the model plays one endless game. Given everything so far, guess the next word. That's it. Predict the next word over and over. So how do we grade a guess? We look at how much probability it put on the word that actually came next. Confident and right, great. Caught off guard, big penalty. We're measuring surprise. Average that surprise across all the words, and that's a quantity called cross-entropy. Fancy name, simple idea. On average, how shocked was the model by the truth? Now here's the part people forget. You don't average that surprise over the whole conversation. Thanks to label masking, you only counted on the assistant's reply. The prompt words get skipped. And that's the point. You're not teaching it to predict the user's question. You're teaching it to write a good response. So you only grade the response. So there it is. The negative sum of the log probability of each correct word given everything before it, counted over the response only. That one line is the whole objective. And here's the signal. The slick answer is, it's the exact same loss as pretraining, just narrowed to the response. Seeing that connection tells them you understand the whole pipeline, not one slide of it. So go compute it by hand, one word at a time until it clicks. The free notebook is in the bio. They slide a pretrained model across the table and ask, "You're gonna fine-tune this. What knobs do you turn and roughly where?" This one separates people who have done it from people who have only read about it. Here's the mindset. You're not raising this model from a baby, it already knows a ton. You're a film editor making small, careful cuts. Nudge it, don't repaint it. That explains almost every setting. First, the learning rate, how big a step you take each update. You go tiny, around 1 to 2 times 10 to the minus 5. That's 10 to 100 times smaller than pretraining, because big steps shove the model off the cliff of what it knows. Second, epochs, how many times you loop over your data. And here's the trap, more is not better. Stick to 1 to 3 passes. Go further and it memorizes your tiny dataset and forgets the wide world it came from. Third, batch size, usually 32 to 128, which averages out the noise so it walks a smooth line. And don't hold the step size flat, warm up gently, then ease it down a cosine curve as you settle in. And the move everyone reaches for now is low-rank adaptation, LoRA. Instead of editing billions of weights, you freeze them and learn a tiny add-on patch. Way cheaper, and it keeps you from wrecking the original. So that's the recipe, small steps, few passes, a light touch. And here's the offer getter, the numbers are one search away. The ones who get hired explain why the rate is small and why few epochs, all from one fear, catastrophic forgetting. They reason from the principle, not the cheat sheet. So go turn these dials yourself and watch what each one does. The free notebook is in the bio. This one has a scary name and it earns it. Catastrophic forgetting. It's the thing that quietly ruins a fine-tuning run, and if you can name it and stop it, you instantly sound senior. Picture someone who's read every book. Now you lock them in a room for a month studying only legal contracts. They get amazing at contracts but forget how to crack a joke or cook dinner. That's catastrophic forgetting. Your pretrained model is that generalist. Fine-tune it too hard on a narrow dataset, and it overwrites the weights that held all that general knowledge. The new skill shoves the old wisdom right out. And here's how you trigger it. Train too many epochs or crank the learning rate too high. Your score on the narrow task keeps climbing so it feels like winning, but underneath, the broad intelligence is draining away. The metric looks great while the model quietly gets dumber everywhere else. That's the trap. So how do you stop it? First, go gentle. Small learning rate, just a couple of passes. Careful nudges instead of a sledgehammer. Second, blend a little original pretraining data back in. It's like making your contract expert keep reading novels on the side, so they stay sharp instead of tunnel-visioned. And third, the clean one, use low-rank adapters. You freeze the original weights so they can't be overwritten and learn a small add-on patch instead. The old knowledge is safe by design. You never touched it. And that's the game, teaching the new thing without erasing the old. And here's the signal, anyone can define the term, but the ones who get hired connect the dots, the small rate, the few epochs, the data mixing, the adapters, all answers to this one problem. So go overcook a model on purpose, watch it forget, then rein it back in. The free notebook is in the bio. Okay, here's a question that opens half of these interviews. A raw language model just predicts the next word. It has no idea what helpful even means. So how do you teach it to actually be a good assistant? That's the whole pipeline today. The answer is a 3-step recipe. People call it RLHF, reinforcement learning from human feedback. And the thing that trips people up is the order. Each phase feeds the next one, so you cannot shuffle them. Think of it like training a new apprentice. First, you show them how the job is done. Then you teach them to tell good work from bad. Then you let them practice while you give feedback. Same 3 moves here. Phase 1 is supervised fine-tuning, or SFT. You take the pretrained model and show it a pile of example conversations done well, and it copies that style. This is the apprentice watching over your shoulder. Phase 2, you train a separate reward model. You show humans 2 answers and they pick which one they like more. The reward model learns from thousands of those choices until it can score any answer the way a person would. Phase 3 is the reinforcement learning part. The model from Phase 1 writes answers, the reward model from Phase 2 scores them, and the model nudges itself toward higher scores, usually with an algorithm called PPO. And here's the part that separates people. Why this exact order? If you skip the showing step, the model has no decent behavior to reward yet, so the practice phase just flails. And you need the judge built before anyone can practice. Each phase is the ground the next one stands on. So that's it. Show it, build a judge, then let it practice against that judge. 3 phases, and out the other side comes something that actually feels helpful instead of just auto-completing. Anyone can list the 3 names. The person who gets the offer can tell you why the order is locked, what each phase actually hands to the next. That's reciting it versus really getting it. So go run the whole pipeline yourself, 1 phase at a time, and watch a plain model turn into an assistant. That's when it really clicks. The free notebook is in the bio. So during fine-tuning, supervised fine-tuning, the model copies your examples almost exactly, which means your data is the teacher, and a sloppy teacher makes a sloppy model. They'll ask what quality issues hurt you here, and there's a real list. Let's walk it. The mental model is simple. The model doesn't judge your examples, it imitates them. Every bad habit in the data gets faithfully copied into the model. So quality isn't a nice-to-have here, it's basically the whole thing. Let's go through what trips people up. Issue 1. Inconsistent formatting and style. If half your answers use bullet points and half are dense paragraphs, if the tone lurches from formal to casual, the model gets a confused signal about how to respond. Mixed messages in, mixed behavior out. Issue 2, plain factual errors in your demonstrations. And this one's nasty. The model can't tell a true example from a false one. It just learns to imitate. So a wrong answer in your data teaches it to be confidently wrong, in exactly that smooth, believable voice. Issue 3, imbalance. If most of your examples are about, say, coding, the model gets lopsided and weak everywhere else. Same with length. A pile of one-word replies or rambling essays teaches it a skewed sense of how long an answer should be. Balance shapes behavior. Issue 4, contamination, the scariest one. Even a small amount of harmful or toxic content sitting in your data can leak straight into the model's behavior. It absorbs that just like everything else. So a little poison in the well goes a surprisingly long way. And here's the twist that flips the lesson. The Lima paper showed that just 1,000 really clean, high-quality examples can match datasets many times bigger. So it's not about piling up data. It's about a small set of genuinely good examples. Quality crushes quantity here. And here's the offer getter. Anyone can rattle off bad formatting, errors, imbalance. The hired answer names the root cause. Fine-tuning is pure imitation, so every flaw gets copied, which is exactly why Lima proved 1,000 clean examples beat a giant messy pile. That framing is the tell. So go fine-tune on a messy set, then on a small clean one and watch the clean data win. You'll feel why quality beats quantity. The free notebook's in the bio. So how do people fine-tune these enormous models without a server farm? The answer is almost always LoRA, low-rank adaptation. They ask about it because it's everywhere now, and the idea behind it is genuinely elegant. Let's get it. Here's the pain it solves. Normally, fine-tuning means updating every single weight in the model. For a model with billions of them, that's a brutal amount of memory and compute, way out of reach for most people. LoRA asks, do we really have to touch all of them? And the insight is lovely. You freeze the whole giant model, don't change it at all. Then beside each big weight matrix you add a tiny little patch that learns the adjustment, like leaving the textbook untouched and just adding sticky notes in the margins. The book stays, the notes do the new work. Now the clever bit, the low-rank part. Instead of one huge patch, you use two skinny matrices back to back. One squeezes down to a tiny inner width, the rank, and the other expands back out. Multiply them and you get a full-size update, but you only ever store those two thin slivers. A fat change, tiny storage. And why can you get away with so thin? Because the change fine-tuning actually needs is much simpler than the full model. It lives in a few key directions, not all of them. So a low-rank patch captures basically all of it. You're spending parameters only where they matter. And the payoff is wild. You end up training maybe 0.1% up to 1% of the parameters. So the memory drops through the floor, training speeds up, and suddenly you can fine-tune a huge model on a single decent GPU. That's the unlock. And two perks worth naming. Since the base model is frozen, it can't forget what it already knew, so you dodge catastrophic forgetting. And each little patch is its own swappable adapter. One base model, a different adapter for each task, snap them in and out. Clean and modular. And here's the offer-getter. Anyone can say LoRA is efficient. The hired answer explains why. You freeze the base and learn the update as two low-rank matrices, because the needed change is genuinely low-rank, so you train under 1% of the weights and dodge forgetting. That reasoning is what lands it. So go add a LoRA adapter to a frozen model and watch it learn a new skill while touching almost nothing. That's when the elegance hits you. The free notebook's in the bio. So they ask you, what's the actual difference between supervised fine-tuning and RLHF, and most people fumble it because they describe the recipe instead of the reason. Let's fix that over coffee. Here's the mental model. Supervised fine-tuning is learning by copying a tutor. You've got example answers, and the model imitates them word by word. RLHF is learning by getting graded. Nobody hands you the perfect answer, you just get told which of your tries was better. So supervised fine-tuning works at the level of single words. For each token, it nudges the model toward the one the demonstration used. That's it. It's fast, it's stable, it almost never blows up. But here's the catch, and this is the trap people miss. Copying has a ceiling. The model can only get as good as the demonstrations you fed it. If your examples are merely okay, your model is merely okay. It can't outgrow its tutor. RLHF flips the level. Instead of scoring word by word, it judges the whole answer at once and pushes toward the ones humans prefer. So it can chase qualities you could never write down as a clean example, like, this reply just feels more helpful. And that's the real payoff. Because it learns from comparisons, not copies, it can actually climb above the demonstrations. It's the difference between do it like this and that one was better, try to be more like that. Nothing's free, though. RLHF is slower, more moving parts, and a lot less stable. You're doing reinforcement learning now, and that can wobble. Supervised fine-tuning is the calm, reliable one. And the thing nobody tells you, it's not a versus. In practice, you do supervised fine-tuning first to get the model competent, then you layer RLHF on top to polish it toward what people actually want. One builds the floor, the other raises the ceiling. So the shallow answer is, one's supervised and one's reinforcement learning. True, but flat. The answer that gets the offer names why it matters. Supervised fine-tuning imitates at the token level and is capped by the DMOS. RLHF optimizes whole sequences from preference, so it can go beyond them at the cost of speed and stability. So go run a supervised fine-tune yourself and feel where the ceiling kicks in. That's when this really lands. The free notebook is in the bio.